My name is Eugene Lee, and this is my Lab 3 report for Physics 2212. So to start off, the purpose of this lab was to use the principles of energy and current conservation to predict the behavior of circuits containing resistors and capacitors in both series and parallel. The models and fundamental physical principles used here were Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law. As a brief preview of results, we experimentally confirmed that voltmeters have very large resistance while ammeters have minimal resistance. And we also experimentally confirmed both of Kirchhoff's laws. So in all experiments, the system was everything in the circuit, including the batteries, wires, multimeters, and resistors, while the surroundings was Earth. The initial conditions for all the experiments were that the battery is disconnected, there's no voltage drop across any component except the battery, and current is equal to 0. For experiment 1, we measured the current at two different places across a circuit that had two resistors in series. The current at the first ammeter was 18.5 milliamps, while the current at the second ammeter was 17.9 milliamps. And we also determined that reversing the ammeter reverses the sign of current. These results are similar to our model in that the model also predicts that reversing the ammeter reverses the sign of current. A difference, however, is that the model predicts that the current in both ammeters should be the same because this is a series circuit. This is probably due to the source of error in this experiment, which are the measurement inaccuracies in the multimeter. For the second experiment, we substituted the first ammeter with a voltmeter, and we measured the voltage at that voltmeter to be 2.8 volts, and the current at the second ammeter to be 0 milliamps. A similarity between our model and this experiment is that the model predicts that there should be zero current through the ammeter because an ideal voltmeter has infinite resistance, meaning zero current would flow due to Ohm's law. A difference, however, would be that the voltage at the voltmeter does not equal the voltage of the battery, which is 3 volts. And this is probably due to the fact that the multimeter isn't perfectly accurate, and also because the battery has already been used a bit, and so its voltage is slightly below 3 volts. For the third experiment, we took out the voltmeter and used it to measure the voltage drops across the two different resistors. We also found out the current that flowed in both cases was the same, and this matches up with our model, which predicts that because the resistances stayed the same, the current flow should be the same. A difference between our model and the experiment, however, is that the sum of the voltage drops across the two resistors does not equal the voltage of the battery. And the calculated voltages across the resistors using Ohm's laws don't line up with the measured values. And this is because of the sources of error, which remain the same as the previous experiment. Here's a graph of voltage versus distance across the circuit. As you'd go across the battery from point A to B, your voltage increases from 0 to 3 volts. Then when you go across the first resistor, your voltage drops a bit. Then from point D to E, you have no voltage drops because we're assuming that wires have no resistance. And then from point E to F, which is going across the 100 ohm resistor, your voltage drops to 0 volts due to Kirchhoff's voltage law. Then from point F to H, again, the voltage remains the same because we assume wires and ammeters are ideal. For experiment 4, we found out that using an ammeter instead of a voltmeter that was in parallel with a resistor led to an overall increase in current. And this matches up with our model, which predicts that because ammeters have much lower resistance than voltmeters, the equivalent resistance of the parallel circuit would decrease, which leads to an increase in current through it. The sources of error again remain the same. Here are the calculated resistances of the resistors. Note that we are assuming the wires and the ammeters to be ideal, meaning they have zero resistance. For the final experiment, we charged up a capacitor that was in series with a light bulb, which was basically a resistor, and then we later discharged that capacitor. We found out that increasing the resistance of the resistor increased both the time to charge and discharge, which lines up with what our model would predict. However, a difference between our model and experiment is that the model predicts that the capacitor should take the same amount of time as it does to discharge, which didn't happen in this case. And this is probably due to the source of error in this experiment, which is that we visually determined when the capacitor was fully charged and discharged. For the what-if questions, if we charge the capacitor with no resistor in the circuit, then the capacitor should theoretically charge instantaneously since current flow would be infinite. However, this can't happen in real life since nothing has zero resistance, including wires. For instance, in our experiment, we determined it took around 0.5 seconds to fully charge. Well, that's it for this lab report. Thanks for watching.